Since we missed a little bit of class, I wanted to go ahead and recap. We didn't have time for discussion on determinants part 2, and so I'll just kind of recap the last part of it especially. A lot of stuff is in the key idea of a lot of stuff is in exercise 5, where we start out with a very simple shape. Here's U and here's V to make a rectangle, a square in fact, and then W is UW is this guy. This guy goes over A. So let's say this amount is A right here. And so here's W. So let me dot all that in actually. So this is most people identified this as what's called the shear transformation. And shears are in some ways the least familiar of the transformations. They're not a rotation, it's not a scaling. But this is where they come in as being super important. Because if you look at the formula for area of a parallelogram, the classic formula is base times height. And guess what? The base hasn't changed, and the height hasn't changed. The way I think of it is this is a stack of books. This a nice sort of rectangular stack of books looked at from the side. And I just push the books over to make it into a leaning stack of books. That doesn't change, it doesn't inflate the books or contract the books. It's still the same cross-sectional area. And so this has not changed at all. And I haven't put in a minus sign either, because I've been continuously sort of shearing this over. It can't possibly suddenly flip from plus to minus. And also, if you look, here's U and here's V, that's clockwise, and here's U and here's W, sorry, counterclockwise. That's still counterclockwise, it's still positive. So even with our weird signed area thing, it's not different. Okay? So, a shear transformation, at least in this example, seems to keep the area the same. Okay? So, if we look at the matrices, people noticed that there's two ways. Different people looked at it a little bit of a different way. This is one of our standard row operations. It's called row replacement. We took a multiple of the top row and added it to the bottom row, namely, well, the multiple was A. And that's producing something with the same area, even the same oriented area. That's interesting. How general is that? It's an example. It's not a proof in general, but we can think about it in general in a minute. The other thing people were thinking about is I'm multiplying. If this is my matrix, well, I don't want to use A, so this is UV, then I take this matrix times the UV matrix. And this, of course, is an elementary matrix. We have this sophisticated way now of thinking about row operations, which is you multiply on the left by an elementary matrix. And some people were putting the A up here instead of down here. If you look at it carefully, it's going to be in this place. Whenever you do a row operation, remember the elementary matrix that does that row operation is you just do exactly the row operation you're thinking of to the identity matrix, which is basically what we're doing here. The other way to think about it is that the bottom row of the left-hand matrix in a matrix product is going to control what appears in the bottom row of the actual product. And it's the bottom row that's getting interesting here. That's a combination of the two rows. The top row is staying the same. If you have the top row of the identity matrix as the left-hand factor in a product, that means you're not changing the top row. It's just going to be whatever the top row is here. So that's why the U stays a U. So, exercise 6 is really about how general is that. So, and to combine it. So that was one very, very special example. We started with the identity matrix, or in other words, the standard unit square. So let's look at a general row replacement. you've got like A, B, C, D, and that goes to, let's keep the first row the same, and let's say C plus KA and D plus KB. Let's think of the back, and it's all geometry still. Let's look at the picture. Well, this is, let's call that vector U, and that vector V. And so this is going to be U and V plus KU. Okay, so let's see. We start out with the UV parallelogram. And now I'm going to keep U the same, but to V I'm going to add a multiple of U. So let's add maybe half of U to V. So that's going to be, I'll put it in thick dashes. That's going to put that right there, and then that's going to go off this direction. And so here's U, and then this is U plus, and the half I just picked so that it wouldn't be completely off the picture or it wouldn't be too small. So let's see what happens here. What we've done is we've taken this stack, what's already a sort of tilted flat stack of books. It's not on a horizontal table, but say it's on a tilted table, and it's also tilted over to make a parallelogram stack of books, but then I just shear it again. I just move the top book parallel to itself. And I move this book a little bit less, and this book a little bit less, this book a little bit less, but I'm just squishing it over, I'm just shearing it. Let's see if, I don't have to use that kind of vague terminology about books, let's look at base times height. If I look at base times height, I'm going to use this as the base for both parallelograms. Drop an altitude from this guy, that's the height of the UV parallelogram, of this guy. But because this tip has been moved parallel to the base, that's what this does. It moves the tip of this V vector parallel to the base vector, because I'm adding multiple to the base vector. It's not going to change the height. And so base times height is the same for both of those parallelograms. And so I'm not changing the area. That's the biggest fact of this whole investigation probably. That's really an utterly crucial thing, is that shears don't change area. And it's going to be true for higher dimensions, it's going to be true for volumes and stuff like that as well. So this means a row replacement operation does not change the determinant. It hasn't changed the area, it doesn't change the orientation or anything, so it's not changing the signed area. And so the determinant of UV is going to be